You can see skies and think about all kind of things. Every day you have a different cloud, so it's never be the same.
In the countryside of Japan in 1944, on the island of Shikaku, a 13-year-old Sukihiro Manabe, also known as Suki, was already seeing warnings in the sky.
In a sense, it was a terrible situation there.
Post-war Japan, struggling economically, held little opportunity for a recently graduated meteorology researcher from the University of Tokyo. Weather prediction was still in its infancy.
You know, at that time, what is a science of meteorology? It's a weather forecasting, which nobody trusts.
But halfway around the world, something happened that would change this. Something big. The world's first computers. During the post-war years, physicist John von Neumann had assembled teams of meteorologists to test drive them, to devise ways to use computers to predict the weather. By 1958, frustrated by the lack of opportunity at home, Manabe said goodbye to Japan and joined a team led by Benjamin Franklin medalist Joseph Smegorinsky in the US. At the time, researchers had success predicting weather locally. Manabe, however, had bigger ambitions. What if he could forecast on a global scale?
To understand the challenges Manabe faced, let's take a look at how meteorologists predict the weather. Forecasters divide the atmosphere into an imaginary 3D grid like this one. They take real-life measurements like temperature, pressure, and wind speed and assign each grid point a numerical value based on their observations. After several days of collecting data, researchers use complex math and computers to find patterns and predict change. 3D simulations like this worked well on early computers for small, localized forecasting. But running a similar 3D simulation on a global scale could take years to complete.
I don't want to design any run which computer is not capable.
One way to lighten the workload a 3D climate simulation might impose upon an early computer could be to reduce the amount of data. Now, we might predict that reducing the amount of data would also reduce the accuracy of the simulation. Makes sense, right? Manabe thought otherwise.
Though it may seem counterintuitive, Suki approached the problem by eliminating two dimensions entirely.
You can never win competing nature with complexity.
Manabe and his team would focus on calculations that we can visualize as happening on a one-dimensional plane, such as incoming and outgoing solar radiation, gases, and how these affected global temperature.
All these numerical experiments you can do fast by one-dimensional model.
He used this newfound speed to simulate what the atmosphere might look like under artificial scenarios, increasing and decreasing the presence of the various atmospheric gases to learn the effects on global temperatures. Nitrogen, oxygen, reducing or increasing their presence had only a small impact. Carbon dioxide, however, was a different story, and Manabe's results were groundbreaking.
When you change carbon dioxide, the temperature of Earth's surface, the atmosphere, troposphere goes up. And then if temperature of troposphere go up, air can contain more water vapor. And that means more greenhouse gas, so it's becoming even warmer.
Manabe discovered that should the CO2 content of the atmosphere double, global temperatures would increase 3 to 4 degrees Fahrenheit. His peers would recognize his achievement as the first credible model of greenhouse warming. Manabe would take his research into greenhouse warming further as computing power increased, pioneering 3D models of Earth's climate which showed how global warming will vary over the planet. To many, he is known as the father of the field.
Uncertainty does exist, but there is little doubt that global warming is indeed happening. And so what we can do now is to try to reduce these large uncertainty.